Hi, we've seen all the curves and spline I wanted to cover in this video series. Now, there is one last thing I want to do with all those curves is that every time I showed you the curves, it was actually in a 2D curves. So every point has X and Y coordinate, and then the parameterization of the curve itself was a t that was moving inside of that 2D space. It could have been a 3D space, so it could have been a curve going through 3D world, would have been exactly the same mathematics. Now, if we want to use those curves to actually encode animation data, what we have to do is go down to a one-dimensional curve. And what I mean by that is that usually if you encode animation data, you will do keyframes. So, you have a timeline, and each few frames you give a value, and then you try to interpolate those values. So that's how usually you see Bezier curves used, a Hermite curve used inside of Maya, all that kind of stuff. Now, the mathematic for those might be a bit different than the 2D case. So I will cover each case and show you what we can do and how we can compute a 1D example to actually have keyframes data. So if we go one-dimensional spline, the first thing we can do is go with the Hermite curve. And a one-dimensional Hermite curve would actually means, the bottom line, so that my x's will be actually my t, so it will be the t that I usually go through the curves, and I get the value as y. Now, the Hermite curves goes between 0 and 1, and one thing I can do if it's only 2 keyframes. So what I have here is my keyframes are separate in key times and key values. So my key times is 4 and 25, my key values is 4 and 2. And so I get the tangent that was normally decided for the curve. And if I render this, basically what happened now is that I have, really my frames, and I've plotted the values that I would get if I was requesting the value at each frame. So I had a keyframe data at my frame 4 and 26. It was 4 and 25, sorry, 4 and 25, and then that's my curve, and you get everything here working properly. To get this to work, what I did actually is to assume that the Hermite curve would be a value of size of 1, and so I compute it as the size of 1, and then I'd scale up the value so I can reach it. The only thing you have to do is that if you take your range and you actually scale it, what happens is the tangent you had would actually stays the same, and so the curve will start to get flat. So the only thing you have to do is that knowing that you scaled your range, so that's my range here, between the two, I use that range to multiply my tangent. So actually I compensate for the fact that I will be stretching the curve I'm computing. So that's how you could do it for one single Hermite curve. Is fairly easy to do. Just remember that you basically stretch your functions, so you actually have to stretch your tangent also. If we go one step further and we go toward the cardinal spline, we will have to do that same kind of concept, but there is a few tweak in there. If I go uniform cardinal spline, meaning that every keyframe, every key time will be at the same range between them. So, my key time here is 4, 8, 12, 16, so it's on a regular grid. I can do the same trick as the one I did for the Hermite curve. I can compute my cardinal spline and I can just stretch it. Now, because the cardinal spline already computes the tangents and the curve for me, in this case, I don't even need to bother about tension, because when you go one dimension, basically that tension factor is useless. You cannot ask a cardinal spline to be linear or curved. When you do one-dimensional, it can only tweak the y values, and the t is assumed to be regular under the hood. So the tension has no meaning. And so if I do this, basically I compute the cardinal spline as if it was just, a kernel spline that was going from 1 to 4, just linear steps inside of my animation. I compute the curves, and then I can stretch it because the tangents has already been computed, the curves have already been computed. I don't need to do anything else than just stretching the end results. Basically, I'm not doing a stretch. I'm just stepping through it as if it was a stretch. So again, cardinal spline, if you're regular inside of a cardinal spline, then you could actually get the values for each frame just by requesting the value properly. Now, if you go non-uniform cardinal spline, then you try to do the same thing, saying I take my entire cardinal spline and then compute it and try to stretch it. What will happen is basically this. My curve will not go through the points if it was really set up on the keyframes. It would assume that actually my t is linear, and then so my t will be, it assumes that my frame is here and my frame is there. So I cannot just do a complete stretch of the final result. What I need to do instead is actually use the fact that I can do the emit curve and I can stretch emit curve, so I can reuse my functions that I had before, which was the one that converts the cardinal spline into a bunch of hermit. And so I could do that, calling the cardinal spline, having the hermit points, and then for each range I can properly stretch them the same way as I did it for the example of the hermit, just by restretching the tangent for each of the range I'm computing. And now I have something that looks correct with all my different tangents, and I get the values that actually on the curve every time when I requested a keyframe. Okay. The next one is doing a Bezier curve. Again, a Bezier curve as one-dimensional might be a bit weird, but then we could do the uniform Bezier curve, meaning that I will have, one Bezier curve is 4 points, and so I have my 4 points properly spaced on my timeline. So I get, again, my 4, 8, 12, 16 to represent my points. And if I do this, I can properly compute a Bezier curve that is actually one-dimensional. So I get my t's down here, and I get my values that go there. Now, you might notice that when we go uniform Bezier curve, it also means that my keyframes are really, my first keyframe is at time 0, my second one is at time 1/3, my third one 2/3, and my final one is at 1. Remember when we did the conversion from Bezier curve to hermit curve, we had to divide the tangent by 3. That's why one of the hints, that's why we have to do it, is because a uniform Bezier curve basically is split in 4 parts. So it's 0, 1/3, 2/3, and 1. So it works if you really put all your points along those values. Now, if you were trying to do non-uniform Bezier curves, I will have the same issues as the cardinal. It would just compute something that makes no sense. So there is actually only one way to do a Bezier curve that you could sample to get keyframes. And that's how every animation package are doing it, is that for this specific case, you actually do a 2D Bezier curve. So instead of having my time at the bottom and my value, what you will have is a 2D Bezier curve that will be time value together. And then we have to find a way to sample that properly to get the value we wanted for each frame. And that's what we call usually the finding y given x. I would first probably execute the example, and then we can explain what's happening, because it will be easier in this way. So when we do a Bezier curve, the t values that goes between them does not represent a linear time in my timeline. So the t value here is not continuous compared to all the keyframe I'm trying to reach. So the thing we have to do is actually try to find the opposite, asking if I want to be to a specific keyframe value, what would be the t parameters of my curve I need to use for that curve to actually be on that spot. And how we do this is by doing the mapping between t and the time, the real time. So I get my t value that goes between 0 and 1, and I get my real time that goes between between 4 and 16. So that's the time that come here, and I get the t down here. And so what you have to do is say, if I wanted to be at frame 10 in my timing here, if I want to be at frame 10, I need to be here, and I need to be able to find the t value that represents my frame 10. And see, it's not 0 or 5 because this is not just a linear mapping. And how you do this is basically realizing that this graph here, when we ask for what is the t there, is the same as moving that graph up and down and then trying to find the roots. So usually finding the roots mean finding where this curve will hit 0. That's how you find a root. And so what you need to do is to say, I want to take the entire curve that was drawn as usual. I want to shift it down 10 frames because I'm looking for frame 10. And then as soon as I've shifted down, I can find my root, and I can know that it will be hitting here nearly something 0.4 or something, right? So that's what mathematically we do. And that's what this function is doing. It takes the time at which you actually want the to evaluate for t, and it computes the Bezier curve with that little minus time I'm looking for, and then it finds the roots. I'm using the root function from NumPy. It's a cubic function, so you can have more than one root. I know that I'm constraining the system, so I can only have one root, or 0 if I'm outside of my animation. But if I'm inside of my animation, I constrain the curve itself to not give me more than one root, so I can just return the first root that will be valid. And to understand what's happening here and how we compute this, it's basically because if I do it with SymPy, again, to go through the mathematics. If I start with the Bezier function as usual, so that's the Bezier computed with the Bernstein basis function. If I expand it all, that's how you compute the entire function now based on x0, x1, x2, x3, and so on. And I know that the thing I want to do is move. It's basically taking the points that I have here. So I get my 4 points here, and to move this up and down, what I will do is actually I would shift all the points here. I would shift it on the side to actually try to bring that 10 right here, right? So what I'm doing now, I would keep the mathematics that actually compute the Bezier curve, and I will say that I want to shift the entire Bezier curve using a substitute. So I replace the x0 by x0 minus x, x1 is x1 minus x, and so on, and that give you that massive functions now, where every x0 is x0 minus x, x1 is x1 minus x, and so on and so on and so on. And if I try to asking to factorize that and rearrange it, you will see that every x cancel each other except the last one. So you only have 1 minus x. So you could keep the entire functions as is and just do a minus x at the end. And that's the beauty of doing it this way. And that's what you have here. Basically, when I find the roots, I find the root for a cubic function that is a, b, c, d, and it's just the d that has the minus x here. So that's how we actually do it for a Bezier curve. It's a bit more involved, a bit more complex, but it allows you to have a 2D curve and to sample it linearly through your time. That's how it's computed usually. And the final thing I want to show you, because it might be useful, is it's good to be able to represent your animation data using one type of curves and that kind of stuff. One thing we might need to do at some point is actually encode your animation data. So it might come from a really massive array of data, and you just want to fit a curve through it and encode a curve that represents your animation data, not as heavily as what you have as input. And so what I would do here is actually fit a uniform cubic B-spline using the minimize system from NumPy or SymPy. I don't remember which where the minimize come from. It comes from, let me see, minimize come from SciPy, sorry, SciPy optimize. And so what I would have is basically a function, and I will draw on the end result so it will be easier. So I have a function that is my orange dots, and that's the function that I would say I want to encode using cubic B-spline. And I get all the points I want to use, the number of points I want to use for my cubic B-spline, and that's where they will be placed. And I get the cubic B-spline, which is the one I've computed. That's how my animation would be rendered if I was using it. So I'm fairly close to my original data. And how you do this kind of stuff is basically by having, okay, I have my function itself, which is now a really complex function that I compute. And then I would say how many points on that curves I would use to try to encode my data. And I said that I would take 20 points around it. I get my B-spline basis. So again, I'm using the formula for the matrix for the B-spline. I have my function to compute my B-spline. And what I would do is I would have a bunch of points. So that's how many points I want to use on my B-spline. I always said I want to use 7 points. And finally, I get the real value of my function. So I sample my function, as I said, 20 times between every point. So that's my, it's all the points on the time, and that's the values of my complex function for all those x's. So I take 100 points on my x, and I compute the y values for those. So I have an x, y values for all of those points. And I have an error function that would just be a square error, a sum of squares. So I will get my points and inputs. So that's really the control points of my B-spline. I compute my B-spline with it, and then I do the sums of the squares error between the two. So it's the usual functions you use to minimize an error. You have to start with an initial guess. So my initial guess is actually to put my points on the curves, to put my control points on the curves. And then I call the minimize with my error functions and my initial guess. And the result itself will give me where I want that x to be. So my result is here, and I get my optimal y value. And then now that I have the optimal y values for all of my points, I can draw my B-spline so I can actually display it. That's how you get this kind of stuff. So it's a optimal uniform cubic B-spline, meaning that if I give 20 control points, they will all be spaced with the same space between them. If you get only 4, that kind of stuff, it's a uniform one. So you don't have more range and more points in one range and less in the other range. Is really uniform. But that's how, in a nutshell, how you would do fitting a curve and any type of spline. If you have different type of spline that you actually want to fit, it would be the same concept. You would use the minimize and try to find the minimal error. That will be the simplest way to do it, thanks to SciPy. And I hope this would make sense for later papers. when I will start to use these kind of functions, and we'll be able to come back to these videos if you ever need to dig a bit deeper into the curves I'm using at some point. Hope you enjoyed it, and see you next time.